we've got a little time, and I can introduce the LeChatelier's lab. It won't take very long because it's an informal lab, which means that you don't have to set up your notebook, and you can make your observations on the hard copy that I hand out, and you then turn that in. This is an informal lab. And that works best for this type of lab because we're going to do a number of different reactions. We're not going to focus on just one reaction. Our focus is going to be on what have we done to change the reaction, and notice the effect and relate that to LeChatelier's principle. So I think short discussion would be in order. If for no other reason, to caution you about taking this too lightly. Just because it's in an informal lab doesn't mean you need to put your brains in neutral. Let's see, going to do 104. Okay. This is 104 L. This is lab number 3. Yeah. That's fun. Just discussion. Is that right? 2 S's in discussion. Okay, I'll tell you what. Let me pull it up and share the document. I got to go find it first. We're good. Okay, I don't need to rehash what LeChatelier's principle is, but we're going to use different concepts to illustrate LeChatelier's principle. The first one is going to be solubility. Solubility is in terms of sodium chloride solution. So whenever you, for chemical purposes, when you're thinking of LeChatelier's principle, you need to have a balanced equation in mind, either in your head or on paper, preferably on paper. And this is the one that we're going to use for solubility. Okay. So this the solution is saturated. Sodium chloride solution is saturated at room temperature, which means it can't hold any more sodium chloride. If you put more sodium chloride into it, it's just going to sit there. It won't look like anything's happening. Now, we know, of course, that solubility is a equilibrium. All equilibria are balancing between rates. So it's dissolving at the same rate as it's precipitating. But this is your controlling reaction. Now, I'll caution you now and probably several times more. When you tell me which way a reaction is going to move with a disturbance, if you say right or left, you must reference a balanced equation. Why? Because I could write this the other way, and then right becomes left. If I don't see a balanced equation and you say it moves right, then I have no idea what you're talking about. Okay? You may think that you are referencing an equation because it's somewhere in that paper. But when you answer the question, you need to put that equation right there where you say right or left. Then there's no mistake. Okay, so what we're going to do to illustrate this equilibrium situation is once it is in equilibrium, then what if we add chloride ions? And remember, this is concentration, not just adding the ions, but increase the concentration, right? So we're going to increase the concentration of chloride ions by what? By adding hydrogen chloride or hydrochloric acid. And this is going to be, let's just say, concentrated. That is, when we add hydrogen chloride in this solution, we're not adding much water. That way, we can increase the concentration. If we add a dilute solution of hydrogen chloride, then we're also going to add a lot of water, and we're not changing the concentration. But if we do it this way, we can increase this value. Now, referencing this equation, the reaction is going to move to the left. It's going to produce precipitated sodium chloride, and you will observe that in the procedure. Okay. The next is one we've seen in a video before. That's solubility. The next one is complex ions. So in this particular case, we're going to add iron in aqueous solution. I think it says iron 3 chloride. And we also have cyanide ion, thiocyanate ions. Okay? And they'll be added as probably potassium thiocyanate. So we have counter ions that are spectators, right? In this one, it's probably chloride, and this one is probably potassium. But this is our equation that we're setting up in equilibrium, and it produces a complex ion. Let's see, the way they write it, they put N on this side, like that, with a 2+ charge. Now, why is it a 2+ charge? Because one of these is 3+ and one of those is 1-. We got a 2+ left over. Now, this is red. This is slightly yellow. So there's a visual contrast between the two. We know that if it's on this side, it'll be slightly yellow. If it's on this side, it'll be red. Or if we disturb this so that we reduce that amount, it'll become less red. Or if we disturb it so we increase this, it'll become more red. That way we can monitor the progress qualitatively of our reaction. So when you write this, when you reference this equation for what you've done to it, be sure you write that equation. Then you can say right or left. Okay, so how are we going to influence this reaction? Well, one way is we can add iron 3+ ions. That should drive the reaction this way to produce a redder solution. Or we can add thiocyanate ions. And that will also drive to the right. What if we want to drive it to the left? If we want to bring it back to the left, we need to remove one of these or add one of these, right? Adding one of these is kind of problematic. So removing one of these is more useful. So one of the ways is we couple a reaction where we add silver. It produces solid. Okay? That removes thiocyanate and drives the reaction back to the left. And you should see a disappearance of this red color plus an appearance of a white precipitate. Okay. I think, let's see. Did we added silver. Okay. Now that we've got this, we can couple it with another reaction and drive it back that way. So what would we do? If we want to remove this so that we can free this up here to drive it back, we need a reaction here. That will remove silver, and this equilibrium will go back this way, producing thiocyanate. Now we can react with iron and reestablish our red color. The other possibility is also for complex ions, we're also going to have the possibility of silver. Let's see. I want to write it the way they do. Okay, solid first. Silver chloride, just like we had there, is in equilibrium with silver plus and chloride minus. Okay? Now, we can see this as a precipitate, a white precipitate. These don't have a color. In order to, let's see, this is going to be derived from silver nitrate, which is completely soluble. So we're going to have this in solution. And if we add chloride as sodium chloride, add chloride, or we could add it as acid. Let me see, how are we going to add that? Hydrochloric acid. Okay, we're going to add HCl here. So we add this combined with that and produces this precipitate. Okay, we establish an equilibrium there. Now, we've produced this white precipitate. How do we influence this equilibrium? Right? Because this is another solubility problem. We're going to use complex ions to influence this one. So we can't remove chloride easily, but we can combine this with ammonia. Right? And that will produce this polyatomic ion. Which is soluble. Right? So what we're doing is we're coupling this reaction with this ion and removing it from solution. That drives this reaction to the right, and the precipitate should disappear. Okay, now we can have acid-base equilibria, which we've talked about already. Let's see, I'm going to make room. Look at the board. Now we can have acid-base equilibrium. In this case, we're going to have a solution of ammonia, and the weak base, ammonia, should produce some hydroxyls in aqueous solution, which means it should give us a basic solution. All right, so once we have this equilibrium established, right, this is a weak base reacting with water to produce ammonium ions plus hydroxyls. So the solution should be basic, and if we drop some phenolphthalein in there, it should turn pink. This didn't give us as much detail as the other. All right. So this is our equilibrium expression. So how can we influence that expression? Well, if we just add some base to it, it's going to make it more pink, right? And that doesn't tell us much. It doesn't show a change in equilibrium, although it will happen. Or we can add more ammonia and drive it further, make it more pink. But what if we couple a reaction so that, let's see, I'm going to scoot down here to the method and see what it is. I can't remember what we added to it. Okay. You can add acid. We add hydrogen ions here. That makes water. Drive the reaction this way. And consume hydroxyls. Eventually, you consume enough hydroxyls where the reaction, the color indicator goes clear because we've used all of it up. We've consumed all the hydroxyls. If you add, okay, that's one way. If we add ammonium chloride, actually as a solid, and it dissolves, it produces this, which increases that and drives the reaction back this way, which does what? It should consume hydroxyl ions and become clear. All right. Let's see. I think that's all. Those are all the equilibrium steps we're going to do. All right. These are PreLab questions. We can do the PreLab questions. Let's see. Did I get a chat? No, I didn't get a chat. All right. So PreLabs. One. All right. What do we mean by a stress applied to an equilibrium system? A stress is anything that throws the system out of equilibrium. Right? And we looked at several possibilities. Change in concentration, change in temperature, change in pressure, and they all have their requirements, their factors that are required. So that stress is anything that throws the system out of equilibrium. So give some examples. Let's see. Well, you could just say change in concentration, change in temperature, change in pressure, which is usually associated with a change in volume. Okay. Now, this change in concentration has to be one of the members of the balanced equation. And change in pressure, the requirements there is that the product moles of gas are different than the reactant moles of gas. How does an equilibrium system behave when a stress is applied to the system? That's just LeChatelier's principle, right? How does it respond? Right? The equilibrium shifts in a way that will mitigate the stress. That's one way of putting it. Okay. How about number two? We got 4 parts. A, B, C, and D. Okay. Suppose you have this reaction. 2SO2, and that's a gas, plus O2, gas. It's in equilibrium with 2SO3, gas. All right. Now, we're referencing this equation, so you can say left or right. Right? It's given. So if the following changes are made to the system, tell what effect they will have on the system, whether it shifts to the left or the right or it doesn't shift. Add oxygen to the system. Add oxygen. What's going to happen? No idea.
It'll shift right.
Yeah, correct. Okay. How about B? Sulfur trioxide is removed from the system as it forms. Same effect, right? Removing a product has the same effect as adding a reactant. How about C? The pressure of the system is decreased. Okay. What we have to do first is evaluate the moles. So this has 3 moles of gas and this has 2 moles. So if we decrease the pressure, the response is going to be to increase the number of moles. So decreasing the pressure shifts left. And D, a very efficient catalyst is used for the reaction. What effect will that have on equilibrium?
None.
0, right? No effect. Now, the equilibrium processes underneath, right in here, will be much faster. But the balance will be the same. Won't change at all. All right, let's see. 3. Answering these pre-lab questions should help you with post-lab questions too. So number 3 says, explain why the solubility of a sparingly soluble salt represents an equilibrium system. Well, we had an example, right? And the one that we're going to use in here. But sodium chloride is not a sparingly soluble salt. A sparingly soluble salt would be something like silver chloride. Right? In the first course, 101, we learned from solubility charts that silver chloride is considered insoluble. But we know now that it's only slightly soluble. We set up an equilibrium with that solubility in aqueous solution. Okay. How does that represent an equilibrium system? The solubility. Think back to what the requirements for equilibrium are. Right? It's a balance of kinetics. The forward reaction rate is equal to the reverse reaction rate. That explains it all. Just because I've got 20 lines there for you to fill out, you don't have to put answers in all of them, right? Just explain what you know to be the fact of an equilibrium system for a sparingly soluble salt, right? The dissolution, which is this step, and this step is the precipitation. The rate of dissolution equals the rate of precipitation. That is an equilibrium system, as described here. Now, number 4, I'm going to let you look that one up yourself. because you need to go do some research for that one. You need to get three things here. Right? The question is, let's see. Find the formula, right? Formula for phenolphthalein. Right? Carbon, hydrogen, oxygen, nitrogen, I think is all there is, but there may be others. Just look it up, write it down. Then give us its chemical name. And that I'm talking about IUPAC. It's going to be it's going to be long as your arm, and you don't have to understand what it means. Just write it down. That tells me that you actually went and looked it up. And the last thing out of this question you want is pH change range. Okay, those three factors are for number 4. Okay, I think that's all the damage we can do today. And let's see. We got a weekend and we got Monday, and then Tuesday we'll come back and do a review on chapter 14 and 15. And then we'll come back on Thursday and have the exam on acids and bases, and then go in the lab and do this lab. Now, you don't have to turn it in at the end of the lab unless you want to. If you want to take some time to think about it and work on it, then you can turn it in the next time we come in for the next lab number 4, which should be the Ka of acetic acid. And that's going to be on the 3rd. Actually, LeChatelier will be next Thursday, and then the following Thursday will be Ka of acetic acid. So I need to give you the method, hard copy, or you can get it from Brightspace. That one's a formal lab, so that one does need to be included in your lab notebook. But that's a week from next Thursday, 2 weeks from today. Next Thursday, we're going to do LeChatelier. All right. Any questions? I suppose we're done for the day then.